Okay, let's start with the content. First, I want to give like a small history lesson on blockchains and all the industry in all. Then talk about more users. Yeah, then as already said, like I want to talk about Jam because like CorePlay, all the ideas to build it on Jam. And I want to introduce some of the building blocks that we are using. Then I want to get to CorePlay, sorry. And yeah, lastly, I want to talk about like infrastructure for these actors. So as most of you probably know, like Bitcoin had like this Genesis block in 2009. From Bitcoin on, like there were like some forks of the Bitcoin code base, like Namecoin, Litecoin, and some others. And it took like 4 years to have like the first non-Bitcoin based blockchain implementation, which was Ripple in 2013. Yeah, I think it already shows. And like if you look at today, like we have maybe thousands of blockchains, but it's like most of them are forks of other blockchains and like forking the code. It's basic. For me, basically, writing a blockchain isn't that easy, especially from scratch, because like you need to have a lot of knowledge. You need to know about networking, storage, consensus. So like a lot of topics if you want to write your own blockchain, which makes it very complicated. So we had the next step in the history of blockchains, I would say, was the invention of smart contracts. They launched or premiered with Ethereum. And today there are like 78 million smart contracts. I mean, not all of them are like different or like, like most of them are probably also forks or like variation of each other. But it already shows like there are maybe thousands of blockchains, but millions of smart contracts, which shows that it's like easier to write a smart contract than to write a blockchain. The good thing about smart contracts is that like the developers can concentrate on the business logic because like as I said, you don't need to networking, blah blah blah. All the stuff is being provided by the blockchain for you. You also get the security from the base layer, so you don't need to take care that like you have enough validators. The validators have enough stake or proof of work or whatever you're using. The bad thing of smart contracts is that you have like less room for optimizations. So like you can for sure optimize in certain ways, but yeah, there's always like an end to it. And for blockchains, it's like you can go deeper when you want to do these optimizations. And you also have less access to certain things, like you cannot change the ordering of transactions or like decide when a transaction can be applied. All these things. So like then we have like this third phase, what I call it. It's like rollups and similar things. I call it similar things because like some people have like really concrete descriptions of what a rollup is, and maybe don't like if you call all the things rollups. But with Cosmos, for example, there exists like sovereign chains connected by bridges. You don't have like any shared kind of security. It's more like that you need to trust all these different chains. Then there was or is Polkadot with parachains, and parachains are like similar to like ZK rollups because like the validator set is actually checking the like the state transition of your in Polkadot case parachain, or like or you prove like your ZK or like verify your ZK proof. All these things that you have, like there's a different security assumptions to all these things. So yeah, and so people are going back to these rollups because like people want to have more freedom. They want to decide like what is the fee model, what's transaction ordering. They want to capture the fees or whatever. All these things. To simplify like these development of rollups, people started providing SDKs to write a rollup, which makes it easier, but it's still complicated and not as easy as writing a smart contract. Also, you don't get like the infrastructure for free. You need to have nodes running, you need to have integrations, all these kind of things, which are provided, if you kind of provided when you have a smart contract by the base layer, you need to have on your own. Okay, now to more users. I think, or like, if you look at the industry right now, like a lot of, like all blockchains want to have more users because more, like all these blockchains should have like a value. It's not like that we just do all these things for no meaning or whatever. If you want to have more users, you need to have better products, more applications. And so that brings us to the point like, okay, you need to have more developers to do these things. You also need to have like people doing marketing and business, but also these people need to have like products and applications that you can actually sell, because like without that application, like just selling it maybe works for some time, but not for always. So if we look at the developer report from last year, we have like 24,000 developers in the crypto industry. So that's like 0.01% of all the developers existing worldwide. So like that's a really small margin of how many people exist in the crypto industry versus like how many developers out there. And it would be actually nice that we could like capture more people, because like the more people we have, the more people or the more things they can build. I think that blockchains are too complicated. Smart contracts going in a similar direction. I mean, it makes stuff easier, but yeah, you need to still think about like, does my computation finish in a block? Does it not take too much resources? All these things which make it quite complicated if you like used to like write your simple whatever Python script or Java script thingy, and like then someone presents you the thing and they get like, okay, what should I do here? Yeah, I think we need to pick up the people where they are and not where we want them to be. So that was like to the introduction, now to the GEM building blocks. So GEM stands for Join Accumulate Machine. It's a protocol written by Gavin Wood. You can find more information on greypaper.com. And tomorrow there's also a talk about it. I think the last one. So the important things for us here is like GEM will provide 341 cores, and all of these cores can execute arbitrary code in a RISC-V based VM. All these cores get the same security level as like the base layer, so as GEM itself from the validators. You will get also deterministic gas metering, which is important because like with that you can implement continuation, which enables you to write an endless loop, because like you can always like stop the loop after some execution time and then always restart from the last point, which makes it much easier to write code. And also another important topic is like synchronous composability. When you have like, or GEM has all these like all these shards. Like you have here, you can have like infinite amount of shards. I mean, not really infinite. There's an upper number, but whatever. And you have like 341 cores, which means like that every step you could like verify like 341 state transitions of all these shards. But that's like if you have infinite number of shards, that's like if you only can like progress 341, that's not enough. So also you want to have that you talk between these shards, and that's like what the synchronous composability will enable you to do, because like you can take like multiple shards and put them onto the same core, so they run at the same time, and you can do like talk to each other. So like what you, for example, have in Ethereum with smart contracts, where multiple smart contracts can call each other. You could have the same on GEM on these cores, and the nice thing is like that the data is sharded and like outside of GEM, but yeah, you can bring it together and like manipulate it together. Okay, now to CorePlay. I copied this nice description on what an actor is from Wikipedia. I think the most important point here is like these actors are like basic or building blocks for like concurrent computation. So basically what we have like all these shards which can run concurrently, and these actors are reacting to messages, so they either send new messages, change internal state, or create new actors. Like there are like a lot of things that these. Yeah. So like that's fitting model, I think. For me, this or like the idea here behind CorePlay is like it's a mix between like blockchains and smart contracts. So like we want to get like these the properties of like the performance of a blockchain, like, or the performance optimizations you can do on a blockchain, the block space you get on a on a blockchain, and like like not really for like more control over transactions and all these things. Like you can get this with like these actors. And on the other side, we also want to give you, or like, or the idea is also to inherit like some features or like some properties from smart contracts. So for example, the logic encapsulation, like if you look at smart contracts, they always do like one thing, like multi-sig smart contract or proxy smart contract. While if you look at the blockchain provides like a lot of things like multi-sig proxies and other things together, which again makes it more complicated and not that easy to stick stuff together and create like a new application out of it. So, and like with these actors, we also hope that like this logic encapsulation goes like that you just build smaller things which can be used together with other stuff. And we want to make it like easy as you start and then like complex if you need it. So like kind of as a smart contract, like it's easy to use, but if you need more and need to drill down more, then you also get these kind of features. Yeah, and we have like a minimal interface, or like the minimal interface requirement. Like there will be like maybe need a main function and like import like a function for sending messages and receiving messages. That's it. And that should enable like, and so CorePlay is not only about like providing like a language, it's also like providing like a framework. So other languages could also be easily integrated into the thing as long as it compiles to RISC-V, which should be almost all languages. Yeah, and it's also like, as I said, like it's also the framework. It's also about like providing infrastructure, because like you don't want to, like for blockchains, you don't want to run all these nodes and all this stuff that should be provided to you to make it easier to get started, similar to how smart contracts are working. Here I've written like a really bad example. I've written some code which should show like a little bit how it looks like in the future. Not everything of that is correct, and also like maybe there are for sure like logical issues in it. So like let's concentrate on like this only call ping function here. So what we are seeing here is like that we call into an like actors can export functions that you can call. So, and here we call, for example, this other ping. So like we call into another actor and want to call the ping method. And this will tell the CorePlay scheduler, or however you want to call it, okay, this actor wants to talk to this another actor. So like in the future, I will need to run both at the same course, so like that this actor can progress, because like it wants to have this synchronous interaction between each other. So by default, like the function that I exposed by these actors are like, assume that you want to have mutable access, so that you want to have these this interaction, like that you need to run both together. But there can also be like read-only functions, which then enables you that you maybe have one actor that you can still run somewhere, but it only do like a read-only, so like it just reads data from its state and provides it back. And then another thing here is like what I call this wake me up in whatever thing is like the actor should have the possibility, because like actors maybe react to messages, but also maybe they have some kind of maintenance work they want to do. And so they should tell the scheduler, hey, please wake me up in whatever, 60 seconds, 1 hour, whatever is required for your logic. So like it's not only like reacting to like outside events, but also being able to like on its own being scheduled in the future. I have here like another example for like what I call a lock actor. So like you could imagine that you have like an actor which is basically functioning as a lock. So maybe you have like another actor which is a database or whatever, and you want to manipulate certain parts of the of this actor space. So like you would first need to lock it. These are kind of free-floating actors. So like the idea is here more that like, or you can call them utility actors, They have no logic on their own, they have no messages or whatever. It's only that they're being used by other actors as an when talking to only used when talking to other actors. Here's it like, or here's it important to have these read-only stuff, because like this one actor maybe wants to lock something, and the another actor then needs to know if this first actor has a lock. I've written here this small diagram for it. So like in this case here, like the actor 1 wants to lock in actor 2, and then it wants to call this change x function, and the change x checks then in the second actor again, hey, does this first actor actually have like the lock? And yeah, so like that's the operations that should be executed. And here's like how you could do that, like how you could schedule this. So the first actor and the second actor, like it's the beginning are like scheduled together, because like actor 1 needs to lock needs to mutual access to actor 2. So both are scheduled together. It can get a lock, and then the actor 3 is right now talking to another actor. And in the second iteration, then like as we have the lock, we need to go and do the modification. So like we have actor 2 and actor 1 and actor 3 actually scheduled together at the same core, and have like these read-only instance of actor 2 also running on core 1, which then only provides like these, yes, have the lock. Okay, now to infrastructure for actors. Yeah, if you have a smart your smart contract platform, you as I already said, like you have like you have all the nodes that run this blockchain, and like you if you want to interact with the smart contract, you send like a transaction to this blockchain, and then like it gets applied in a block. For Gem, it's a little bit different, because like these actors are validated in core, like outside of the block, and you only like commit the final state result to the Gem block. And Gem has no idea how these actors are working, how you can communicate with them. Yeah, so you need to provide these state transitions actually to Gem, and not like only transactions. Also, other properties you have is like when you have these actors, they maybe have state, maybe the state is in the DA layer, or maybe the state is somewhere outside or whatever. Someone needs to take care and keep the state around. You also need to have this solver thingy that will be able to, okay, you have like these 5 actors, and like some actors want to talk to each other, and like other actors maybe don't need to execute now, maybe another actor needs to be executed in 1 minute, and all these kind of things. So like you need to have a solver available that can, where you can like give it like, these are the requirements, and it gives you like a work plan that tells, okay, that's now what we do, and then next iteration we do it in a different way. I also try to show that here, like you have these users, and like the users are sending like these transactions to these nodes, and these nodes are then not like Gem nodes, but like these extra network of nodes for driving these actors. And like then you have here like at every node, like every time, like one node, for example, is leader that does the work plan, and yeah, then moves forward. Yeah, another thing that I think would be nice, or like what we want to have then, is like an AWS for actors. As I told you, with these, like yeah, maybe actors can schedule themselves to be executed in like 5 minutes, 10 minutes, or whatever. Someone needs to pay for it, because like in the end, like you're still running on a blockchain, so like someone needs to pay for it. And it would be nice that you, for example, you have like your actor, and you can buy like these blockspace in advance, where it gets like maybe like these every 10 minutes, or like 1 week of block space or something like that. And then like this amount gets always reduced, and then it can maybe fill it up on its own, or like people are paying for it, or like it's like on demand, either, for example, paid by users, or paid by users, like you send a transaction, by that you also pay for it. or like on demand, you're paying it for users, and like to have actually like free execution. Yeah, that's it, and thank you.
Thank you very much, Bastian. Thank you for everyone who already asked questions. You still have a little bit of time if you want to add a question, if you want to upvote some questions. But I'll ask you the most upvoted question first. Here goes. Are actors tied to a shard?
Yes. So actors are like what are called like shards in this gem view are like actor would be one shard.
That was nice, quick. We have the next one here. Oops, I might have just put the wrong one. You said you can run many actors on one shard at the same time. How many actors can be run on a core? What are the limits?
I mean, that in the end depends on like what like the computation you want to do. So like you get a certain amount of computation per core. Like you also get like memory, or data you can input, and like you need to fit all this data together. So like it's complicated to say what is the actual limit. Like if you maybe have like 10 actors and each actor just does like 10 milliseconds of execution, then you can do 10 or 100 or whatever. So that fits. But if each actor is doing like complicated mathematical computations, then you cannot run 100 per core.
I found the question that I accidentally marked as answered. Why 341 cores? 33 by 11, but why?
That's a question you can ask tomorrow to give. But I think it's because like there are 1,023 validators, and like there's a reason with, I think with the data sharding or something. Like I don't exactly know, but you can ask tomorrow.
Okay, great. Yeah, Gavin is speaking at 5:30 tomorrow at the main stage, so you can save that question there. We have another one here. How can actors on different shards interact if shards cannot call each other synchronously?
I mean, shards can call each other. Like, if you want to have the synchronous interactions, you need to have one guy that like takes both of these actors and puts them together on one core and does the execution together. So yeah, does that answer the question? I hope.
Okay, then we have this one. Can actors execute in parallel on the same core given that they are not dependent?
Right now, not. Maybe in the future, but it's cores are right now like more like single-threaded execution. So like what that would mean is actually that maybe you could just double the amount of cores, and then like each validator, for example, runs these in parallel, and then like you kind of achieve the same as running them in parallel manually or whatever you want.
Okay, I think this will be the last question. Are actor nodes responsible for transaction ordering as well?
That's kind of the idea, or like at least that you can give them like that you can get access to. So for example, like the transaction, like the messages, what you could do is like maybe you like iterate over like there's like 100 messages coming in, you just consume all of them, and then like internally you order them in whatever way it fits your needs or something like that. So that's like a little bit blurry right now, but it should be possible to expose that in a way that you can do that. But by default,